Can you find the slope of this? What about this? Or that?
That first one was probably easy, but what about the other two? Other than the involuntary how, you might have also asked where. And for this napkin, you might even have asked in what direction.
To answer those questions, we'll use derivatives. I'll show you how they work and just how useful they can be.
Of course, you'll remember the slope formula from your algebra class. And you might also remember the derivative from your introductory calculus class, which allows you to find the slope of any curve at any point.
But what happens if we move to 3D? What if we try to take the slope of a napkin? This is where we use partial derivatives and the gradients. You might have noticed I said partial derivatives. This is because, unlike a 2D graph, we can't describe the whole slope with just one expression.
We know that slopes go left to right on 2D graphs, but on a 3D surface, it's not really defined which way slopes should go. So, we have to break the derivative into multiple derivatives, one for each direction in the coordinate plane, and each one describes a part of the whole slope. So for example, this stands for the slope in the x direction, this stands for the slope in the y direction, and this stands for the slope in the z direction. Adding them up gets us the gradient, or the total slope, at that point. You might have also noticed that each partial derivative is a vector, shown by the unit vectors being multiplied to each derivative. The partial derivatives only tell us the slope along their respective axes. To get the total slope at a point, we have to take their vector sum. This is the gradient.
Because the gradient components are the partial derivatives, which represent the greatest change along their axes at any point, the gradient tells you the net direction of greatest change at any point. It's basically telling you where a ball would roll if it was dropped there. Partial derivatives are very useful in science since they can be used to describe almost anything, and justifiably, they show up everywhere, from quantum mechanics to population modeling and even the stock market. Now you know that partial derivatives, while they look scary, are just slopes in 3D. Simple but very powerful math.